Today we're going to discuss how polarization happens in macroscopic samples of conductors and insulators. Let's start with insulators. Recall we discussed the example of what can happen to a neutral atom when an electric field is applied. The electrons and nucleus shift relative to one another, thereby forming an induced dipole with electric dipole moment P. Now the drawing shown here vastly exaggerates the shift, which is typically tiny compared to the size of the atom. In other words, the atom behaves as an insulator. The charges that comprise the atom are not really mobile, can't move over long distances. A macroscopic sample of an insulator, say a piece of plastic, behaves essentially the same way. In other words, imagine we start out with an insulator which is composed of many atoms. For simplicity's sake, let's assume the sample is neutral and that there are no permanent dipoles in the sample, something like this. When no external electric field is acting on the sample, there is no polarization. However, if we apply an external field, let's assume the external field is uniform in space. The charges that make up the atoms do not move large distances, but they shift slightly. Let me emphasize here that even if the external field is turned on essentially in an instant, it takes a bit of time, typically nanoseconds, for the shifting to occur. If, after turn-on, the external field is steady in time, then after the shifting is done, the macroscopic sample will have a steady, non-zero electric dipole moment P. Let me point out here that the net electric field inside the insulator is not equal to the external field because the polarized atoms in the insulator generally contributes significantly to the net field inside the insulator. We'll discuss later what happens to the net field, but for now, keep in mind that in general, the net electric field inside the insulator is not equal to the external field, and the net electric field is generally non-zero. Now let's look at an example involving a conductor. Let's consider first the case of an ionic solution, like salt water, where the solution is neutral, zero external electric field is present, and has zero permanent dipole moment. Note that in the case of aqueous solutions, the water molecules each have a permanent dipole moment, but are oriented randomly, so overall the ionic solution has zero permanent dipole moment. The sample is in equilibrium. There is zero net electric field inside the sample, and the positive and negative ions for salt water, sodium and chloride ions, respectively, are distributed uniformly. Let's now imagine we turn on an external electric field. Let's assume the field is uniform in space and, after turn-on, constant in time. Then, at the very beginning, the ions will experience an electric force that will cause them to move. In this example, positive ions move to the right in the direction of the external electric field. Negative ions move to the left in the direction opposite to the external electric field. After a very short time, this will cause polarization with a buildup of charges, something like that shown here. This polarization will itself lead to a vector electric field, E sub p, that points roughly in the direction shown. The net field inside the solution is the vector sum of the external field and the polarization field. As long as this net field is non-zero inside the solution, charges will continue to move in response to the net electric field, until eventually the solution is sufficiently polarized such that the net E field inside is 0. Let me emphasize, the external field has not changed. It is the same as it was right after we turned it on. The ions moved until the solution was polarized enough to produce the polarization electric field, E sub p, that is large enough and pointed oppositely to the external field, such that the total field, the net electric field, is 0. The solution reached this condition in a very brief time interval, within nanoseconds after the time the external electric field was turned on. At this point, we say the solution is in equilibrium and the solution has a well-defined, steady electric dipole moment vector P solution as shown. The polarization will remain as shown as long as the external field remains turned on and steady. Let's now look at another example of a conductor, a piece of metal. We can think of a typical metal, say copper, consisting of positive ions located at fixed lattice sites and a sea of conduction electrons. Let's assume the metal is uncharged and initially there is no external electric field and no permanent dipole moment. So initially the piece of metal is unpolarized. Now when we turn on an external electric field, the conduction electrons shift in the direction opposite to the applied external electric field. The positive ions remain fixed. The shifting conduction electrons lead to polarization of the metal that very rapidly, within nanoseconds, leads to the same equilibrium condition we discussed before. The net electric field inside the conductor, which is the sum of the external field and the polarization field, equals 0. The conductor has a dipole moment, P, that remains steady as long as the applied electric field remains turned on and steady. Let's try to answer two questions about polarization. A glass of Brawndo, an ionic solution, is placed near a charged tape. Which diagram best shows the polarization of the Brawndo? Pause the video here and try to answer the question before continuing. In this question, the tape acts as the source of external electric field acting on and polarizing the Brawndo. Now figures 1 and 2 suggest the Brawndo behaves like an insulator, where at the atomic or molecular level, the charges shift only slightly without moving large distances. However, Brawndo is an electrolyte, an ionic solution, which we know is a conductor. So diagram 3 is the only one that shows this, and, moreover, shows correctly how the Brawndo would polarize due to the external electric field from the negatively charged tape. Let's ask a follow-up question. Once the Brawndo reaches equilibrium, what is the direction of the net electric field at location X? Pause the video and take a few seconds to answer the question before continuing. It's always true that the net electric field is the sum of all electric fields. In this case, there are two sources of electric field. E tape, the tape's electric field, and E sub p, the electric field from the polarized solution. In equilibrium, these two contributions add to 0. So the correct answer is number 9. In equilibrium, the net electric field inside the solution has 0 magnitude. A final comment. In equilibrium for a conductor, the external field is not blocked or in any way changed. The external field remains the same for a field that is constant after turn-on. What happens is that the external field inside the conductor causes the conductor's mobile charges to rearrange themselves in just such a way to produce the second field, a second field, the polarization field, such that the superposition, the sum of the fields, add to 0 inside the conductor. I want to add a note of caution. The electric field inside a conductor is 0 only in equilibrium. We'll look at non-equilibrium examples, such as currents in wires, at a later time. We have a few more things to say about conductors and insulators. We'll do that in our next lecture.